anytime you have questions, and I'm happy to slow down or to try to clarify or anything like that. But all right, with that throat clearing out of the way, I want to talk about a project.
Can I just add a quick thing which I forgot to add? We are recording this talk, and I hope that's okay with you, Pete. I think you said yes, but just confirming again. And also for the audience, if you don't want to be recorded, then just please let us know, or just raise your hands or type it in the chat. That won't be in the, and then I can read it out, your questions or clarifications.
Sure, that's just fine. Being recorded is not a problem.
Thanks.
Great. Okay, so with that out of the way, I want to talk about SugarCoat, this project that we're using at Brave to improve compatibility in filter lists. So as a little bit of background, as I'm sure most people here know, an increasingly large number of people use content blockers on the web. And not only are they useful for improving your privacy or performance, but they're also advised by U.S. security agencies as a way to improve security in browsers too. So they're important, and they're getting more important. They're not just a matter of making web pages look nicer. And because they're so important, they're increasingly shipped and increasingly implemented. So sometimes they're implemented at the browser level. Firefox ships some, Brave ships a whole lot. And then also extensions do. Maybe the two most aggressive are uBlock Origin and AdGuard. But all these tools and all these tools and many others use filter lists to decide how to protect users, or how to improve users' browsing experiences. And at a very high level, a content blocker is just something like a firewall. It receives information about a request that's about to happen on a website and returns a yes, I should allow this request, or a no, I should not allow this request decision. So at some level, they're very simple, but when it comes to deploying them in a practical way, things get complicated fast. Filter lists largely pull from, or content blockers like what Brave uses and uBlock Origin and many others, mostly pull from crowdsourced filter lists like EasyList or EasyPrivacy. These are just textual lists of a large number of things that look like regular expressions that describe URLs, sometimes with additional filters. So you can say block anything from this URL, but only when it's describing a script, or only when it's a third party or something like that. But they're text, they look like regular expressions, and they're mostly making decisions over URLs. As a side note, EasyList is the largest and most active of these projects, and the main maintainer of EasyList works at Brave to do this full time. So it's something that we're really committed to, and really committed to supporting in other projects as well. So just to kind of give a little intuition of how this works is something to build on through the rest of the talk. So Reddit's obviously a popular website, and a content blocker would be applied to Reddit, something like this. The browser would inform the content blocker that it's about to request the Reddit logo. It would provide some metadata about the request, like what is the host of the request, what is the host the request is being made against? What is the origin of the page that's making the request? What is the context of the request? So is it an image, a script, something like that? That information would be fed into the content blocker, and the content blocker would say yes or no, or something like that. In this case, there's no filter list match for this request, so the content blocker says allow the request through, and the logo gets fetched. And this isn't just true of images as well. It can be true of other types of requests the browser makes as well. So when you're using Reddit, your browser is kind of constantly polling for new posts using Ajax, and those requests are also going through the content blocking engine. So every time your browser polls for show me more requests or more posts, I mean, the content blocker is going to say, yes, this is a request I should allow. Sometimes though, pages will include requests that aren't wanted or aren't valuable to users. So as a toy example, say DoubleClick, which is Google's advertising arm, or one of Google's advertising arms, has a script called ClickTrack. It's embedded in Reddit. This information gets fed to the content engine, or content blocking engine. The content blocking engine then consults the filter lists that it's been loaded with. In this case, finds a rule that looks like this, that says block ClickTrack when it's fetched from DoubleClick, and we'll say block the request. So using this kind of information, the intuition I want to convey here, or the high level information I want to convey here, is using just this relatively simple information of the request, where it's being made, and what's being requested, is almost all the information that content blockers have to decide yes or no. So content blocking is useful, but is it complete? And of course, I wouldn't be wasting your time if it was. Content blocking has a lot of problems, and I'll talk through a couple of them right here. The most significant one, though, is compatibility. So take things that are both unwanted, but also, or are both unwanted in some ways, but also useful in other ways. So in this example, Reddit embeds Google Analytics. Google Analytics has a script that does analytics-y kind of stuff. Some of those things are tracking related. Some of those things might be page beneficial and user benign. And so in this case, just as before, we'll feed the information for the request into the content blocking engine. Content blocking engine will consult the filter list, and we'll get a decision that says, yeah, we should block this. Seems like what we want, but in practice, if we block it, the page breaks. And the reason the page breaks is because here's a very toy implementation of Google Analytics, but it has to do with the page expecting certain functionality to be in place that the script provides. So if we take this very toy version of Google Analytics, that's just this one track function, and all this toy example does is define a global object and stick this track function on it. When a page tries to integrate it with it, it's going to expect that code to be there. So it's called making a call against ga.track. That's not going to be there in this case, though, because we blocked the script. And so now all the code, that's going to throw an exception, and all the code in the rest of the script isn't going to fire. And the result of that is going to be that Reddit doesn't load correctly and users are angry. And probably what it means is they're either going to go to a different browser or they're going to turn off their content blocker. And so they're going to lose all the privacy protections they wanted in the first place. So content blocking broke web compatibility. Is that okay? And the answer is, of course not. So what can we do about this? What are the kind of tools that before SugarCoat, content blocking authors or filter list authors or privacy focused tools had? One is just to make exceptions. And this is a very blunt but very obvious kind of approach. So in addition to having a whole bunch of ways of defining rules for what gets blocked in filter lists also have syntax for saying, definitely don't block these things. So you can think of it as anytime something blocks or something a URL matches, anytime a request matches a rule that starts with double @ it means definitely don't block it even if the request blocks something else. And so the rule that you see in the lower right-hand corner is saying, don't block Google Analytics when it's fetched from reddit.com. And so in this case, because the request is being fetched from reddit.com, Google Analytics will be fetched because this rule undoes the previous rule, and the script will get allowed, and as a result, the page is unbroken. So exception rules. They have the upside of being an effective way of unbreaking websites, and they're also extremely easy to write. You can learn this syntax in 5-10 minutes probably. But they come with, and as a side effect of that, there's a lot of them. So if you look at popular filter lists, they're lousy with these exception rules. They're all over the place. But they have a non-trivial harm, which is basically they undo the whole point of the tool in the first place. If people are installing these tools to unblock or to prevent privacy harming scripts from being fetched on fetched in their browsers, well, the exception rule is explicitly undoing that. So this isn't a great approach. This is a kind of last-ditch effort kind of thing. So what else can we do? Another option instead of exception rules is to do something called resource replacements. And resource replacements work by, instead of blocking the request or allowing the request, they give filter list authors kind of a third option, which is to say, instead of blocking the request or allowing it, let's instead replace it with an alternate implementation. So if the original Google Analytics looks like this and had our toy track function in it, we're going to build a fake Google Analytics that has a lot of the same shape. It looks like it has functions with effectively the same signatures, but we just scrape out the privacy harming parts. And so the things that were harmful before now become no ops. And so these replacement versions of scripts are called resource replacements. And so when we go to Reddit now, instead of loading the original Google Analytics, we're now loading this alternate implementation of it. And as a result, there'll now be a ga.track function. It won't do anything, but it'll exist. And so the code won't throw an exception and we can get to the parts that we want. And as a result, you'll see rules like this that say, instead of blocking Google Analytics, redirect the request to this fake Google Analytics script. And when that happens, the content engine knows, okay, don't block it, don't allow it, replace it. And as a result, the page will work again. So resource replacements, how do they fare as a kind of general strategy here? They have the upside of being also repairing compatibility. That's great. And they also prevent the privacy harm that people were seeking to prevent by installing the tool in the first place. But they have a pretty significant downside, which is they're extremely difficult to build, particularly for large scripts and particularly for scripts that are updated a lot. So these aren't the kinds of, this isn't like in 5 minutes or 10 minutes learn the syntax of filter lists. This is, you know, have an engineering degree or have significant experience building real world JavaScript code and how to kind of reason about heavily obfuscated, heavily minified code and how to reverse engineer it, that sort of thing. So very few people, but compared to the number of people who can contribute to filter lists, very few people can build these resource replacements. And not only do you have to build it once, but you have to build it, you have to maintain it over time. So every time the library that you're targeting gets changed and has a different API surface, you might need to update the resource replacement too. So it's not a one-time cost, it's an expensive ongoing cost. And as a result, these things are really difficult to build and very difficult to maintain. And so there's relatively few of them. But we have, this kind of points towards a way forward. So we have this, we want the ease to deploy of exception rules, but the privacy benefits of these resource replacements. And so maybe we can automate this. And this is the intuition that SugarCoat is building from. How can we automate the generation of these privacy preserving resource replacements? And so that's what I'll talk about in the rest of this talk is how do we do that? And how do we know if we're doing it well? How do we automate these privacy respecting resource replacement scripts? So at a high level, the idea here is relatively simple. Instead of trying to rewrite the entire script, maybe all we really need to do is just find the functionality that's built into the browser that can do privacy harming things and replace those. So we don't have to understand what the entire script is doing. We just have to find the kind of APIs the browser provides that allows code to kind of break out of the V8 sandbox and interact with the outside world. And once we find those, we can rewrite the code to replace them with privacy preserving alternatives that effectively no op. And then if we can prevent the script from interacting or reaching outside the JavaScript sandbox, then we'll have prevented the privacy harm. Okay, so kind of the structure for how I want to walk through this. Like I said, it seems simple in practice, or it's simple in concept and complicated in practice. I'll first talk through how do we define what behaviors in JavaScript or in the browser that we need to rewrite. How do we enumerate those? I'll then talk about once we know what we want to replace, what do we replace them with? Third, I'll talk about okay, well, we know what we want to replace. How do we actually find those in deployed script, given how minified and obfuscated and dynamic JavaScript can be as a language or application target? Then I'll talk about, okay, we know where we want to replace things. How do we actually rewrite the scripts? And then last, how do we evaluate if we've done a good job? So I'll go in that order. Okay, so what is it in deployed JavaScript that we want to rewrite? Well, if JavaScript operates mostly in a sandbox that doesn't have mostly doesn't have I/O, well, we'll just target the things that do I/O, and we'll target the things that do I/O in patterns that we don't like on the web that seem privacy harming. And we largely break these into two categories. Recall that most of the time JavaScript looks like this. It's JavaScript talking to JavaScript. It's not talking to the outside world. It's not persisting outside of the JavaScript context. Those things only happen when you start working with additional APIs that the browser provides to the JavaScript language. And so these category one is storage APIs, ways that JavaScript code can persist values across executions. And so those are through APIs like the ones you see on the left: cookies, local storage, session storage, DOM storage, IndexedDB. There's many others, but they all look like this. The second category we care about are ways of doing network. So even if I've just stored a value that doesn't necessarily harm the user or harm user privacy, we need someone, the page needs someone to communicate that back to a server somewhere to actually kind of close the loop. And so we also target these network APIs that allow the page to talk to servers. And so, or to put it differently, we target the ways that identifiers are stored and the ways that identifiers are exfiltrated. I'll just add here, this is me bolting something unattractive onto Michael's slides. But we also initially thought we wanted to target these APIs that are very common for browser fingerprinting. And you absolutely could. There's nothing in the, it would be relatively simple to extend SugarCoat to do so. The reason we didn't is that Brave already provides strong benefits and strong protections against this kind of fingerprinting. So for our practical purpose, it wasn't so useful. But it would be trivial to extend SugarCoat to also target these APIs or any other APIs that you cared about. It just wasn't as useful for our case. But you should, I think without error, you can consider the SugarCoat approach generic enough to apply to any of these APIs. Okay, so that's step 1 of 5. How do we decide what functionality in the browser do we think is privacy harming, or at least privacy risking, privacy threatening? And so we have these lists of these APIs, and now we have to figure out, well, what do we actually do instead of those API calls? And what we do is we build these alternative implementations of those APIs. So if in the Google Analytics example earlier, we were trying to rewrite the entire Google Analytics script to be privacy preserving, here we realize that we actually don't need to do most of that. Most of that is non-beneficial work. All we really care about is rewriting the API calls that I mentioned before, the ones that do storage and the ones that do network. And so, for example, we'll replace the browser's fetch implementation with this no-opy kind of thing, where regardless of how the browser calls it, we can let pages call this function, and it's never going to touch network. It's going to no-op. And we just replace the browser's implementation of fetch with this version of fetch. And we can do this for all the APIs that we discussed before. And the one benefit of this is, unlike Google Analytics example, where we had to rewrite things for every single script that we targeted, here we just have to rewrite we have to write one of these mock versions of each of these APIs once, and then we can reuse them across every script that we target. So there's some amount of work up front, but it's fixed and it's reusable. So the cost amortizes really quickly. Okay, so those are the relatively easy parts. What don't we want scripts to do, and what do we want them to do instead? Now I'll start to go into the more complicated parts, which is, okay, well, how do we find the textual parts of scripts that are actually doing those things? And you might think that in some languages this would be a relatively easy problem. You can do some static analysis. You can find just the strings in the text that say local storage or equivalent things. But because JavaScript is so dynamic and so flexible, that's extremely difficult to do in JavaScript, and you're not going to be able to do it through static analysis alone, or maybe through static analysis at all. So instead, what we do is we use this dynamic approach by building on this browser instrumentation Brave has built called Pagegraph. Pagegraph is this very deeply integrated into Blink, V8, and Chromium system that we have that allows for high resolution attribution or high confidence attribution of page events to their actors, their actees, and what's actually happening. And so we build up these large graphs of page executions of just statements over and over again saying, this script did this to that image, the parser did this to that piece of text, et cetera, and we get this very dense graph of events that allow us to understand after the fact what happened during a page's execution. This has been an extremely useful tool that we built up and maintain at Brave that we've used in a lot of projects. And if this seems like it might be something that's of interest to a project you're working on, I'd be happy to talk about it more, either as part of this talk or afterwards. But there's some pretty meager documentation about this online that I maintain. But to just get some very, very simple intuition of how Pagegraph works, like as I mentioned, it's just a large series of actors or things that are doing things in pages, actees or things that are having things done to them, and events, which are the edges that attach the two. So actors are nodes, actees are nodes, and events are edges. So we might have as an example of something that might get recorded in a page, we might have a node that represents a piece of JavaScript running or a code unit that's running, and we might have some metadata about it, like the V8 ID for it, the type of script it is, whether it's a classic script or a module script, where the script came from, whatever. And so we have this script node. We might also have another node in the graph that represents a thing that got fetched from network. And so here we'll have some metadata that says where it got fetched from. In practice, we'll also have the type and the hash of it and that sort of thing as well. And if we want to record in Pagegraph a script injecting an image into a page to fetch, to induce this network request, we might do so like this. We'll have some additional node that represents an image tag on the page. We record that the script inserted that image tag in the document or into the DOM, and we note that that image tag then induced this network request for this thing over here. And we can do the same thing with API calls. So if you want to record it in Pagegraph, every document that made a call to local storage will have some node that represents local storage in the graph. We'll have further some node that represents the JavaScript action of getting from an object. And then we'll note that which scripts made those API calls against which APIs. And significantly here, we don't just, or as part of this project, we extend Pagegraph to not just record the information I've just discussed, but also the textual locations in the JavaScript code where these calls were happening. And so sometimes these will be window.local storage, windo.local storage or whatever, but often there'll be aliased versions of that have been passed around or are 18 steps from anything that looks like the string local storage. And so the point is that we can use this system to concretize API calls despite how dynamic JavaScript is. And so we can get these these accurate understandings of which strings or which variables in the JavaScript code were actually used to make these invocations, which seems small but ends up being enormously useful. And if we do this, and so if we do this enough, we can, after the fact, after we've executed a page, we can go back and build up documents like you see on the right, which just say, for every script I see in the document, I want to know everywhere local storage got called. I want to know everywhere document.cookies got called, everywhere fetch got called, etc. And so we can, after the fact, figure out for each script we had, what are the concretized textual locations of these invocations. And again, it sounds simple, but when you're dealing with JavaScript that looks like this, which is far from the worst JavaScript you'll see on the web, this becomes extremely useful and extremely not obvious how you would do this otherwise. Good luck finding which of these, which text strings in here refer to local storage without a whole lot of manual analysis. Okay, so there's more to it than that, but that's the the 80% of it. That's the high level intuition of how we find which textual parts of scripts are making the invocations of the things that we care about. And so once we know where the targets are, how do we actually use that information to rewrite the scripts to generate these privacy preserving alternatives?
Pete, can I ask a question here?
Oh, please, yes.
So what happens if one of these scripts uses something like eval to create a JavaScript string on the fly, and then maybe even obfuscates it using some kind of translation or something, and then runs it?
Sure, yeah, so the way SugarCoat handles that is, the fact that eval is being used doesn't complicate things at all, because Pagegraph just records the eval script as another script that was executed by the parent script. The slightly difficult part is that we don't have text that's fetched from network, at least directly to transform, but that ends up not being a problem because we can capture the text that's being put into eval and save that as a constant and feed that into eval instead. And so the only place this gets complicated is if you have some if someone is dynamically generating the script that goes into eval, and then you have some difficulty doing that because yeah. And so absolutely, if someone's doing that, then we end up needing to do effectively taint analysis to figure out where that string came from, and that's not impossible. But the reason we didn't push things that far in this project, although we started to at the beginning, is that we figured if people were trying to avoid SugarCoat at that level, they're doing it in the wrong way. They might as well just change the URL in the first place. Like there's far easier ways to avoid these systems than that. But yeah, I think it's a fair point that with some level of determination, you're still going to be able to avoid that, although at some performance cost to your code. But totally an important caveat for sure.
Thanks.
No problem. Yeah, if there's any other questions, please, I appreciate it. Shout or let me know, and I'm happy to try to clarify. Okay, so now we have these textual offsets in the code, and we want to do this rewriting. We have, at this point, kind of the target APIs that we care about. We have these alternate implementations of them that we want to swap out for them. And so how do we actually put these things together to generate a new script? And it seems simple, but because we have all these kind of weird scoping rules and these variable scope variables for var in JavaScript, that and other kind of just things that make this not obvious or make this tricky in practice, I want to walk through at least some of how we handled some of the difficulties here. So say we have this get tracking ID function that we want to rewrite. We've already concretized the places where this is happening. So we already have these text role offsets just from the dynamic analysis. And from that, we can learn the parent function scope that we want to target just by doing AST analysis. And so the first thing we do is we find the highest level of scope that we can use to wrap the function, the target invocations. And so we wrap this in the try-catch block. At the top of the try-catch block, we'll do some rewriting code so that what actually is being done there to rewrite it or replace isn't given here, but you can think of it as just replacing the global singleton implementation of local storage with our mock privacy preserving implementation. So after replace gets called, window.local storage now points to our alternate implementation of local storage. When the script actually gets called, or the target invocation happens, they're now calling our implementation, which effectively no ops, or in the case of local storage, just stores it in JavaScript space as an object instead of persists it to disk. This continues to get to work correctly. They can set things to it and read things to it given our implementation. But once the scope leaves, we inject this finally kept block to restore the original state of local storage. And so this is how we prevent side effects from escaping the function, because there'll be other pages or other scripts in the page that we don't want to rewrite, and we might want to give them access to the true implementation of local storage. So we want to prevent side effects from escaping this rewriting process. And so once this ends, or once this function's done being called, local storage now points back to its original implementation, and other pages on this, other scripts on the page are unmodified or run the way that the author expects them to. But by doing things like this, there's more clever things that we do here, or more kind of corner cases we have to handle async scripts and things like this. But it's all building from this kind of general approach right here. But by doing this over and over again, we can thoroughly rewrite these scripts to get these privacy preserving alternatives. Okay, so that's the 80% explanation, or the high level overview of like kind of how the system works. Now, I'll very quickly, before wrapping up, talk about how we evaluated it to know whether we're doing it correctly or whether we're covering everything we want to cover, that sort of thing. And we did an evaluation. There's more evaluation in the paper than I'll discuss here, but I'll talk through at least 3 ways we evaluated the correctness of the system. First is just
to confirm, you require somebody else to tell you that this is a tracking script, because you wouldn't be able to distinguish a good script from a tracker, right?
Right. So we use, that's totally right. And the way we do, that's an additional labor that happens. So those annotations are already in Easy.
Yeah. Okay. Yeah. It's cool.
So we use EasyList as ground truth and then build off that to assist the EasyList authors.
Yeah.
So yes, so we have, but exactly as you were saying, we have these large list of scripts that the EasyList authors have already indicated are privacy harming, but necessary for the page to work. And so this gives us a kind of corpus of evaluation scripts. And so what we do is we run Pagegraph and all these target scripts that are known to be privacy harming, but page necessary. We measure how many storage calls and network calls happen in their unmodified versions, which is the central column. And then we measure whether those things are still happening in the rewritten version of those. So this is just like a very simple, dumb evaluation of are we effectively preventing all the API calls in the script that we mean to, and we find that we are. We're doing it correctly. The system works as expected. But then we want to zoom out a little bit and see, okay, well, that tells us something about the page, but are we actually, maybe things are breaking, maybe we're not replacing scripts correctly, maybe something else is going on. Are we actually effectively reducing the number of calls to network or storage that happen during the execution of a page or during the execution of an application? And so here, if the relevant measurement here is to compare the red solid line and the green dotted line, which give you the reduction in network calls that happen between the dotted green pre-rewritten version and the solid red rewritten version. So that the space between those two curves is the reduction in network calls that happen in the pre and post rewritten versions of the scripts. And the purple and the blue lines do the same thing for storage. And so the gap between those two curves shows the reduction in API calls that we make. And the reason this graph is important is You could also just show that you could also just prevent API calls by breaking every page, right? You could just throw an exception at the start of every page, and that would make your privacy numbers look great. But it wouldn't be an effect. It wouldn't show that you were actually doing what you wanted to do. And so this graph shows that we are, suggests at least, that we're able to effectively distinguish between wanted calls to these APIs that are happening in unlabeled scripts and privacy harming calls to these APIs that are happening in these target scripts that we want to rewrite. So again, doesn't 100% tell us that we're doing it perfectly, but it is one more kind of piece of evidence that suggests we're accomplishing this correctly, or we're doing what we think we're doing. And then last, before finishing up, the third way we evaluated this is with a human evaluation. We had 6 very grateful, or sorry, very kind grad students help us out with this, who helped us manually evaluate these scripts. So the way we did this is we found 50 websites that had exceptions or had known breaking issues on EasyList. So these are 50 websites where EasyList authors or people filing issues against EasyList said, this page breaks when EasyList is breaking this page, and then somebody later said, okay, well, if you make an exception to this rule, then the page unbreaks. So we have 50 instances of websites that are broken and 50 rules that break those websites, or at least in the estimation of EasyList authors. We then, for each of these 50 pages, had 2 of our 6 evaluators randomly selected independently evaluate the pre-broken, the original version, so the version of the page with the breaking script in place, and the SugarCoat rewritten version. And so that gives us 3 evaluations. One is the broken version, one is the version that EasyList fixed by just doing the exception rule, and the third is the version that SugarCoat uses, which is doing the SugarCoat generated resource replacement. And then we have them each interact with the site for a minute and give us a 1 through 3 rating of the page. So 1 means that the page seems to be working perfectly, and 3 means the page is severely broken or unusable, and 2 means something in the middle, maybe images are missing, something doesn't seem quite right, but I'm still able to do what I want to do. And the result of this evaluation is given in this table, but the important part is the bottom half of the table. So to walk through this table, what this means is when blocking means we're just blocking the script. This is the broken version of the page. We can see a lot of our reviewers are pretty clearly able to identify that, yes, the page is actually broken. Those closer to 3, the number is, the more evaluators thought, yes, this page is definitely broken. And when we give them the SugarCoat version instead, the evaluators find the page works perfectly or almost perfectly. Closer to 1 is perfect. There's more measurements like this in the paper to give us more confidence that we're doing this correctly. But I hope these 3 points give you some confidence that the system is actually operating correctly and doing what we promise it's doing. Okay, so with that, I will wrap up. But I want to just mention one other thing, which is, so this is a system that's actually deployed in Brave right now. We ship these resource replacements. We make them available to other projects, uBlock Origin, Firefox, AdGuard, maybe other projects at this point use these resource replacements, and so we're eager to share with them. They're all open source, and they've been an extremely useful tool in protecting Brave's privacy, Brave user privacy. And with that, thanks very much for letting me talk with you all. I'm happy to take any questions you have, or answer any question, or talk more, ramble about someone else. Or yeah, thank you very much.
Thanks a lot.
Thank you very much, Bill. It was a very good talk.
Any questions? Well, people are thinking. I have one, which might be, the answer might be that there isn't much difference. But have you looked at what the manual replacements performance is in terms of page load times, or the total size of the replacements, or any other measure of performance?
Yes, so we have numbers about this in the paper, and I bet I can find them here. So here's the performance numbers in terms of memory, and you find that there's very little difference between the rewritten versions and the original versions. We didn't compare against the manually created versions because those mostly don't exist. There's only 27 of them, so there's not much to compare against. But these are compared against the original implementations, and we find that pages operate very similarly. And there's another one that, here's time differences, and there's one other one that, is it this one? And that's another compatibility one. Anyway, yeah, so we did do some performance evaluations, and we found that performance is negligible to not noticeable. Their performance differences are not noticeable.
Have you observed agents trying to reverse engineer your approach to bypass it?
We haven't because, well, for two reasons. One is it's all open source, and so they could do an easier job than having to reverse engineer. We'll send them the code. But more seriously, or more to the point, if people want to circumvent this approach, the thing to do wouldn't be to get really clever and kind of go down in the weeds of what SugarCoat is doing. The thing to do is just to avoid the filter list rule in the first place by monkeying with the URL or something. So the point, we had some comments from reviewers actually about this paper about saying, yeah, couldn't somebody circumvent this? But I think that's missing the forest for the trees a little bit, because every filter list rule is trivially circumventable. And so we take it, SugarCoat rules are no more or less circumventable than what's already going on in the world. But yeah, if somebody wanted to get around a filter list rule, it wouldn't be difficult. It would just be tedious for them.
And in terms of how much additional reach you're able to have in terms of number of trackers blocked and things like that, would the manual blocking get you 80% of the way anyway, or is it that there's so much changes happening all the time with the scripts breaking your manual replacements that you do need something like this?
So both. So the scripts, I mean, the 27 resource replacements that projects like uBlock Origin ship and Brave ships that are manually crafted are, not chosen at random. They're Google Analytics, they're Google Tag Manager. They're the most common ones. So those probably those almost certainly get you the head of the distribution. But the important thing to consider is, even if there's a power law for these kinds of things, the web is huge. So even if you're, you're 5% into the power law distribution, you're still impacting millions of users. And so it really is important to get these kind of, the 30th most popular tracking script in the web is still going to hit millions of people every day. And so it really is important to get down in some of these things.
Sure.
A bit of an orthogonal question. Do you have an idea of what level is unacceptable for a user in terms of pages broken by Brave?
Yeah, I mean, so that, I think, well, this is something we struggle with all the time, because Brave does a bunch of kind of weirdo stuff, or things that other browsers don't do to try to be very aggressive about protecting privacy. And yeah, it's a knife edge of how much breakage do we think is acceptable for how much privacy gain. And the truth is, it's really hard to say. Like, our early adopters are people who love monkeying with settings for the most part and don't mind if a page being broken is a challenge to be solved, right? But as we get past 50 million users and look at 200 million users, or a billion users, or some whatever real numbers or bigger numbers, people's willingness to unbreak pages on our behalf is going to shrink towards zero pretty quick. And so the answer is, some users are highly tolerant of it and almost enjoy it because it's a sign that Brave is doing something on their behalf, and other people have no tolerance for it. And so it really depends on systems like SugarCoat or some other systems I can talk about, or that are under development right now, to let us not have to trade those things against each other, to have privacy and compatibility at the same time. Because yeah, people's willingness differs widely.
Piers has a question.
I'm sorry?
Oh,
I think that Piers has a question.
yeah. Hi. Yeah. Thanks. Yeah, I was just wondering. Interesting system. I just wondered, because with the fetch, you kind of implement the fetch as a kind of null function. But what happens if there's a kind of return value that the kind of thing's looking for? Then what happens there?
Yeah. So if somebody's fetching something and it has high confidence about the shape of the return value, then probably a page could still break. That doesn't happen with the other APIs because we mock them out to look like they're operating from empty storage or whatever. But the network ones are a little bit tricky. In practice, though, it doesn't end up being that big a deal, though, because at least for large scale applications and web scale trackers, they need to be able to handle cases where the server is down, or where the real world cases where they might not get, where the network isn't doing what they expect it to do, and so they need to code defensively as it. So in practice, we don't see that as a we haven't really noticed, or we haven't noticed that at all being an issue. But I'm sure there are scripts in the world where we'll trip over that. But thankfully, but yeah, in practice, it hasn't been an issue.
Okay, that's good to hear. Also, I guess, I mean, probably none of the trackers use WebSockets, but I don't know whether you thought about the kind of implication of WebSockets.
Sure. I mean, yeah, we don't target WebSockets just because they're not used, but they're rarely used.
Yeah.
But WebSockets, there's web transport. There's ways that pages interact with. I mean, to take your point, there's just a large and growing number of APIs that can do network these days.
Yeah.
WebRTC.
Yeah.
Etc. Yeah. And so all those things could be rewritten. Most of those APIs could be handled in the exact same way, just by generating new mocks and doing that, a one-time cost. What really gets difficult though is when people are interacting with the DOM or interacting with servers through DOM manipulations, because it becomes very difficult to distinguish those from benign page actions. And so, for example, Google Analytics doesn't use Ajax to communicate to Google servers or use fetch. It creates an image object and assigns values to the script attribute to send messages back to Google headquarters. And those are much harder cases to handle, which is why we need this kind of manually curated Google Analytics option. But yeah, anyway, I'm rambling a little bit, but the point is most network APIs can be handled by this approach pretty trivially, but there are some cases because of how the browser works that are difficult.
Okay, and also just to follow up, whether it could be used for sort of security purposes, like detecting malicious scripts or disabling effectively, or sort of defanging.
Sure, I think absolutely, but I think the stronger approach there wouldn't be trying to rewrite harmful scripts on the because if you know something truly is like, you know, breakthrough memory isolation kind of dangerous, you don't want to rewrite it. You probably just want to block it outright. But we had a similar or related paper at S&P 2021, I think, where we do this. We have a different way of detecting malicious scripts based on not on the URL and not on the contents of the page or the contents of the text, but on signatures generated by event loop turns in the JavaScript engine. And we can use that to notice when this is malicious but has been rewritten or is coming from a different source. But this is something I already know about, and so I'm going to shut down or I'm going to block it. I think that approach would be much more useful for an extremely security conscious user than SugarCoat, which is really designed to kind of to get you more privacy without breaking things, but isn't meant to be like a high confidence firewall or that sort of thing.
Okay. And does Pagegraph work with the WASM?
Yeah, Pagegraph works just fine with WASM, because WASM, after it's interpreted, gets executed in V8 just in most ways exactly as classic scripts or module scripts do. So because it's all dynamic, Pagegraph it doesn't make a difference at all to Pagegraph how those functions got into V8 or into V8 bytecode. Just that they're there.
Thanks.
No problem.
I think we have a question from Animesh. Animesh, I don't know if you want to turn the mic on and ask it yourself.
Yeah, so I want to ask how this proposed approach is helpful for operations in web services, which are being integrated with JavaScript. Means how we can explore this approach for this operations in web services. So there are various user resource identifiers for resource state transfer from one state to another. So have you explored this?
Sure. I want to make sure I understood your question. Are you saying could this be used not by a browser user but by somebody a developer who's building a web service? Is that
means whole architecture means backend plus that front end?
Sure. Yeah. So this is, I think this is a great idea and something we've actually been talking a little bit with Cloudflare about, which is exactly the same approach could be used for somebody who's building a web service, not just consuming it. So say that you are integrating, I don't know, what's a toy example? I'm about to deploy a script to a website. I want to make sure that Facebook doesn't ever learn a user identifier. I could use SugarCoat to rewrite Facebook's code on my behalf and then deploy that modified version of Facebook on my page to do the exact same, to get the exact same privacy properties that a browser might want, but in this case, a website wants to protect itself from other scripts operating on the same page. The exact same approach would work. And so you could do the same. You could also do the same thing in Node World or something like that. We haven't tried applying it there, and the number of APIs and shape of those APIs differs a little bit, but the same approach could absolutely work. You could do the same kind of Pagegraph dynamic rewriting. I think that would scale, or that would work.
Any other questions from anyone? If not, thanks, Pete, for the wonderful talk.
Oh, thank you.
And
And for everyone, next one is going to be KK Ramakrishnan on in the last Friday of March.